Okay, we're happy to have Yuzhang Wang. Do you pronounce your last name Wang or Wang?
Wang.
Wang, that's what I thought. Okay. We're happy to have Yuzhang Wang here from CMU, and he's going to be talking about towards practical machine learning with differential privacy and beyond.
Thank you for the introduction. My name is Yuzhang Wang. I'm from Carnegie Mellon. This talk is based on the joint work with Steve Feinberg and Jing Lei that I work with in Carnegie Mellon. So here's what I'm going to do today. I'm going to quickly talk about the motivation and describe what differential privacy is for the sake of just getting everybody on the same page. Then I will talk about two of my work on differential private machine learning, and after that, talk about how that motivates us to consider a weaker notion of privacy called on-avg KL privacy and describe its properties. All right. So let's get it started. So in the big data era, companies, governments, and all the data agencies are collecting a whole bunch of personal data. And for instance, on Facebook, in your Snapchats, this is the QQ in China, and companies are keeping track of and recording down all these user data when you interact with their web services and then try to use it to maximize their profit. And governments use it for other purposes. But the point is that these are all personal data, and people have different level of comfort level about like other people using this data. With all this data, there are a lot of things people can do. For instance, we can use the data to come up with better medical care, more personalized education, and solve all the persistent social science problems. And several decades of research of machine learning, and like maybe 100 years, slightly more than 100 years research of statistics has given us a whole bunch of tools to try to make sense of the data, model the data, and draw conclusions that will make the world a better place. But there's just one catch. With the increasing public awareness of the privacy concern and maybe some new privacy law, it becomes harder and harder for researchers to get the data to actually make all these good things to happen. For instance, the second Netflix prize for movie recommendation was canceled in response to a lawsuit regarding the privacy concern. And slightly more recently, in New York City, when they released the taxi data, immediately it got de-anonymized by someone online, by someone who actually graduated from Carnegie Mellon, and yeah, so all these things highlight the need for formal methods with provable privacy guarantees that protect individual level data. And at the same time, like we have to also recognize that sometimes maybe it's not the best idea to release the raw data in the first place. So we need new ways to interact with data sets. So there are many approaches of doing that dates back to the 50s and 60s in the statistics community. Most of this involves anonymizing the data by removing personal identifiable features and doing k-anonymity and things like that. The thing is, with appropriate site information, this kind of heuristic way of getting privacy can be really tricky. And they are really fragile under appropriate whenever some site information is available. Yeah, this is what's happened with Netflix when people use like an auxiliary data set for IMDb, and they managed to almost exactly reconstruct the one-to-one mapping from users to users, just using their behavioral data alone. And such site information are much easier to get in the context of big data era. what differential privacy do is that it assumes that we are playing against an adversary. And differential privacy makes no assumption on the power of the adversary. It can have unbounded computation and arbitrary site information. What differential privacy does is to, instead of having the adversary to access the data directly, we now have an insulator between the data and the adversary. And the adversary can ask questions interactively, and a curator is supposed to somehow randomize the response, so that if the adversary do not know the random outcome is oblivious, for instance, like in the term that's used in TCS, it cannot possibly identify any individual user. So let me illustrate differential privacy with just one simple example of who likes Justin Bieber. Suppose.
I was just raising my hand.
Yeah. Okay. All right. Yeah. Suppose we have a new special interest group about music, and there is a poll. Do you like Justin Bieber? Yes and no. You don't have to answer this. And everybody responded anonymously on this web portal. And at the end of the day, the final outcome is released. 30 people in the New England lab said yes. Yeah, this might be a bit surprising to everybody, but since everybody answered anonymously, there's no reason to hide your preferences. Like, I would just trust this result. So I came in today as a visitor, and Jennifer is kind enough to allow me to participate in this special interest group. And I did. And we repeat the same poll, and everybody responded, and the answer now becomes 31. So although I have no idea, but my privacy, meaning that my dirty little secret that I actually enjoy Justin Bieber a lot, is now known to everybody in New England.
I answered no yesterday, but I changed my mind.
Yeah, that's a fair point. But suppose everybody answered faithfully, just like the previous day. Based on the site information that's known to everybody, is that yesterday it was 30, and I'm the only one that joined today and responded to the poll. Like essentially everybody knows my musical preference, and this might sound pretty amusing at a glance, but it can be something else. Like instead of the music taste, it can be like suppose this is a poll about the study for financial transactions, or maybe it's a study on the sexual assault on campus. Then just identifying whether individuals responded to the questions can be harmful to that particular person. So how would differential privacy resolve this problem? So instead of releasing just the outcomes directly, it randomizes outcomes so that all we get is a sample from this distribution. So this serves as a smoother of the outcome, so that if you look at the two distributions that centers at 30 and 31, suppose we add a large enough noise, it becomes harder and harder for people to tell which distribution it actually comes from. And that gives a bit of deniable, like plausible deniability. Like in terms of statistics, this adds fundamental difficulty in distinguish between the two distributions based on the Neyman-Pearson lemma. And the noise level that we need to add is proportional to the sensitivity of the count function. In this case, it's just 1. Again, when we release these results, aggregate results in the differential private way, it's impossible for any adversary to infer with enough confidence which distribution, which world this randomized outcome is from. And we can quantify how different these two distributions is with epsilon, which is what we call the privacy loss. Formally, suppose we calculate the log likelihood ratio at every possible outcome h, and differential privacy requires that if we take all possible outcome and if we take all possible data sets that differs by only one individual, this log likelihood ratio is bounded from above uniformly by this fixed constant epsilon. All right, I just want to highlight that there's these two supremums over here. So there are many convenient properties of DP, composes over small groups. Suppose we want to protect privacy of 2 persons instead of 1, then it just aggregates on this privacy loss. It also composes adaptively on multiple access on the data, and it's also close to post-processing. So this is a information processing equality type of result. And typical algorithms are just either adding noise, adding Laplace noise will give you pure differential privacy. Adding Gaussian noise will give you epsilon delta differential privacy when delta is a cryptographically small probability of failure. And there's also a more general approach of randomization through the so-called exponential mechanism where this Q is some quality function. So instead of just adding noise to the outcome, like this can be applied to cases when adding noise doesn't really make sense. Like when we sample from this distribution, we simultaneously guarantees epsilon differential privacy and approximately maximize this utility function Q. So let's get to the to the actual part of my research on differential private machine learning. Instead of releasing just a single number, so in machine learning, we make use of the data by feeding it into a learning scheme. It can be just a classifier, it can be some unsupervised learning, and output some representation of the data. It can be a function or it can be represented by a vector of coefficients. Differential privacy, the scheme of differential private machine learning, instead of just learning this naively, you can use a randomized algorithm so that such that the outcome satisfies differential privacy. So the horizontal axis is a domain of all possible outcome, and the vertical axis is a probability. Just to make it more concrete, let's consider an example of recommendation system. So in model-based collaborative filtering, say Netflix, it uses the data set, which we denote by Z, of the form of who rated which movie with which star, and use a randomized algorithm to come up with a model. And then later people can use this model as a web service to predict their movie preferences. In this setting, we trust the service provider, meaning that we allow Netflix to have the true data, so it's not an adversary, but other users that makes use of the web service can be adversaries. And since A is differentially private, prediction is considered post-processing, so that's secure to the data people use to train this model. Before I go any further, I just want to highlight the high-level idea of the synergy between learning and privacy. So privacy and learning are not completely separate tasks. For instance, if we try to build a classifier to distinguish between cat and dogs, and we use the simple linear separator, and this gives us a compact representation of the decision boundary. And in some sense, F is parsimonious, and that suppresses the private information. On the other hand, suppose we train a more complex method, like a neural network or a kernel-based method, sometimes it's prone to overfitting. And sometimes we say that the trained classifier memorizes the entire data set. So that term alone would tell us that knowing F would mean something that you have already breached the privacy of individuals. Yeah. So it's not completely orthogonal tasks. So privacy and learning are united by the fact that neither task would like to come up with some results that memorizes the data set. So it's well known within the community of differential privacy that if any algorithm, learning algorithm is epsilon differentially private, that implies that the generalization error is bounded from above by epsilon as well. And this dates back to the very early days of differential privacy. So the
empirical risk?
Oh, yeah. Empirical risk is supposed to come up with a hypothesis H. The empirical risk is the evaluation of that hypothesis with respect to the loss function on your training data. And the risk is the expectation of the loss function on new data.
So give an example of that in the case of Netflix, for example.
Yeah. So the risk can be just the mean square error of your predictive stars of movie preferences. And empirical risk is the expected the mean square error evaluated on the training data set. Yeah. So this generalization measures like how well your algorithm would generalize to new data. Yeah.
So does you need to make assumptions that the data are generated by ID or something, or is it just proof in general?
If it's IID, then the risk is for every data point, and if it's like the more of structural loss, like you don't when you are using differential privacy. Yeah, but usually in the statistical learning setting, you do assume IID, but an unknown distribution.
That's what I'm saying. So this theorem is not true. I know that for absolute differential privacy, there's no assumptions, it's just a definition.
Right.
But to have this theorem which you have there, you have to assume some distribution for the learning.
Yeah, you need to assume the data is drawn from a distribution. Yeah.
Where's that from?
Yeah. Depending on whether it's IID, the risk and empirical risk are calculated differently. Yeah.
Does the loss function matter here? Is this true for any? You're saying this is true for any loss?
Any bounded loss. Yeah.
So not necessarily mean square error.
Right. Yeah. For mean square error, it's tricky because you also need to constrain the domain so that it's bounded. But say for 0-1 classification error, then you don't have to assume anything. Yeah, so the first fundamental question that we ask is that what can we learn privately? So the question addresses for every given learning problem, is there a private learning algorithm that is consistent in a sense that as the number of data points goes to infinity, can we converge to the best possible model that's representable within the given class of models in this machine learning problem?
So does learning privately imply that if I change my parameters, the outputted learning function is the same? Like if just one data point in the training set changes, I don't know what you.
Yeah, it doesn't have to be the same, but the distribution that is drawn from needs to be sufficiently close.
With probability 1 minus epsilon.
Right. Yeah, the log likelihood ratio of the two output distribution needs to be bounded from above uniformly by epsilon.
So if I'm trying to manipulate a learner to classify me as MIT student acceptance, this if it's epsilon differentially private, I wouldn't be able to manipulate it very well. Change its classification of me or my people like me.
Right. Right.
Oh, interesting. You're thinking that this provides robustness to the game.
Yeah, it is very much related to robustness, and in both game theory and also in the statistical robustness. So this ignores the sample complexity for any given learning problem. This is just a yes and no question, and this was previously studied in pack learning like a while ago. So we consider a generalized view of this learning problem. So instead of just the binary classifications in discrete domain, the Vapnik's general learning setting contains a remarkably wide selection of learning problems, including supervised learning, unsupervised learning, density estimation, and even some of the modern learning paradigms like matrix factorization, like robust PCA, matrix completion, and other learning tasks. Yeah, neural nets. Yeah, neural nets too. But it doesn't contain these sequential learning paradigms like reinforcement learning and online learning. So let me just quickly go through the notations for statistical learning. The data domain is either, if it's unsupervised learning, it's just Z. If it's supervised learning, it's a feature and label pair. And the hypothesis class is pre-specified by the to define this learning problem that's given by H. And there's a loss function that maps every hypothesis and every data points to a real number. This measures how well this hypothesis represents this very given data point. And the task of machine learning is statistical learning is to try to find the hypothesis that has low risk. And by risk, I just mean it's the expectation of the loss function for a new data point joined from the same distribution. So what is learnability? Again, learnability is that the existence of a learning algorithm such that the risk converges to the best possible risk representable from the class H with a uniform risk of convergence. Yeah. And private learnability requires that the problem to be learnable by a epsilon differential private algorithm. And similarly, we can define epsilon delta learnability when it's learnable by an epsilon delta DP algorithm, and delta goes to 0 at a certain rate with respect to n.
Can I assume that you have also differential private and still that this converges to 0? It seems sort of counterintuitive. I would think that you will have to be forced to have at least some error explanation.
Yeah, it affects the rate, but suppose the number of data point goes to infinity and this epsilon is a fixed constant, then you can always, as the number of data points gets larger, you can most likely, not always, converges to the optimal risk.
But the effective privacy is n times epsilon by n, which is the number of times you vary, right?
Yeah, just consider a very low-dimensional model where the output space is like a bounded compact domain that's d dimension. And suppose the naive learning would typically give you, for square error, the d over n rate. So it goes to 0 agnostically. And suppose you add epsilon differentially private algorithm to try to learn it, and it will be a randomized algorithm, but in expectation, like this additional randomness is fixed, but the number of data points would go to, yeah.
It's just an asymptotic
Yeah.
statement.
Yeah, it's just an asymptotic statement. Yeah.
Sort of I mean, morally, just if I have a lot of people, then keeping one of the differential privates will not conform my algorithm too much.
Yeah. Yeah. It has a lot to do with stability, which measures how much different the risk is when you change one data point. So here's our result. We characterized the private learnability for Vapnik's general learning setting. And for every given learning problem, we now have a crisp statement that if the problem is learnable, is equivalent to the existence of an algorithm that asymptotically minimizes the empirical risk. Yeah. So the converse of that statement is that if a problem for every problem you cannot possibly find a private algorithm to minimize empirical risk, then that implies that the problem is not learnable in the first place. Okay, so when when I told Cynthia about this, her response is that, is this a positive result or a negative result? So I'd say it's a bit of both. So the good news is that now we can, when we try to find a private learning algorithm, it simplifies the pictures quite a bit. We can just focus on privatized empirical risk minimization. If it fails, then nothing will work in the first place. This motivates us to come up with a practical generic algorithm for DP learning. So in standard statistical learning, what we do typically is to minimize the regularized empirical risk. And this R is a sequence that depends on n that goes to 0. So asymptotically, this is empirical risk minimizer. And using either union bound or uniform convergence argument, you can show that this result is well behaved and it actually learns the problem. So in the private setting, what we can do is to use exponential mechanism. Instead of minimizing the regularized empirical risk, we can sample from the exponentiated distribution. And since many of you guys are statisticians here, this is essentially sampling from the posterior distribution if you model the data using a Bayesian model. And if you just drop this, it's like sampling from the likelihood, exponentiated likelihood. Pi of h is any given prior. It can be a flat prior, so you don't have to specify any prior. So anything you specify that's independent to the data.
We'll just modify.
Yeah, yeah.
Because he said that's the loss function.
So pi is like the exponentiated negative log r. Yeah.
Oh, I see.
Yeah.
So that's going away.
Yeah.
Well, no, wait, processing gamma.
Yeah. For gamma equals to 1, then this gamma can be used to tune how much privacy that you need. When the gamma is setting to be something that's really large, then it converges to just empirical risk minimization. And if gamma is set to be something small, then it flattens the distribution, so we get more privacy.
How does one sample from this distribution?
Say it again.
How does one sample?
So
in general.
In general, I don't know. You can use Markov chain Monte Carlo. In practice, when this L is a convex loss function, then there are results that says that sampling from this distribution is you can do that in polynomial time by running Markov chain Monte Carlo.
But the result from your previous slide was it had nothing about efficiency. You didn't care
No,
about efficiency.
yeah,
It was just
yeah,
about
I wasn't.
to
Yeah.
learn, and you don't care about the rate of epsilon.
I should have said that in the previous slide. Yeah. So by the result of McSherry and Tower, when the loss function is bounded, suppose this loss function is a average of the empirical loss or the sum of the empirical loss. In other words, when this boundedness assumption is true, then sampling from this distribution will give you differential privacy, in some sense for free, because that's what people are doing in Bayesian learning in the first place. All right. So we show that posterior sampling is asymptotically normal, when the model is low dimensional. Of course, there's also this regularity conditions. By efficient, we mean that it's nearly optimal. It nearly matches the Crimea raw lower bound up to a multiplicative factor of 1 plus b over epsilon.
This is not efficient in the.
It's not. It's not it's statistical.
Not computational.
Yeah, it's sample efficiency.
It's sample efficient, not computationally efficient. Yeah.
It means that not suppose b and epsilon are both constant, then it matches the lower bound up to a multiplicative constant. B is the boundedness from here, and you can adjust what epsilon is by tuning this gamma.
Yeah.
Okay.
And this is strange, because you say for low dimensional models, but B has nothing to do with dimension. So now I can send dimension to infinity.
Yeah, dimension will go to Crimea raw lower bound. It comes in the Fisher information.
Oh, I see.
Yeah. So it's like the semi-definite ordering.
So, but it seems to me that it's always 1 plus b over epsilon.
So what does it mean?
Independent of dimension.
What does it, like, what's the form?
It's a multiplicative bound. So the dimension would go to, like, the dimension will affect the non-private learning and private learning in the same way here.
But the theorem doesn't involve non-dimension. Am I correct? The dimension doesn't enter your bound.
The dimension does enter the bound if you write the bound in terms of the empirical risk, the access risk. Say it again.
What does she's asking what sample efficiency is?
Okay, sample efficiency is that sample efficiency means that are you making the best use of your data, like in terms of the non-asymptotic sense. Yeah. So there's this Crimea-Roll lower bound that says that.
So in terms of the number of times I called, like, look at a sample?
No. In terms of the number of data points that you have.
So to get the same mean squared error, using posterior sampling, you would need this factor many more samples. Right.
Yeah, basically that's that. Yeah,
So
suppose you do the non-private learning.
Theoretic lower bound,
Yes.
how many samples you need to sort of produce a certain error, and this says you can work within a factor 1 plus b over epsilon of that information.
Right. Yeah,
So
you can
it's
just use more data to.
not just 1 plus b over epsilon.
Right. Yeah. For non-private learning, it's like 1, and if you need privacy, it becomes 1 plus b over epsilon. Like sometimes there are ways to even get rid of this term, but not in general. Yeah. So we can actually sample from the previous objective using an approach called stochastic gradient longevity dynamics, which basically simulates a stochastic differential equation. And besides that, it's differentially private asymptotically if it mixes, as we showed previously. Even if it does not mix, we can use advanced composition and subsampling lemma to construct an approximate differentially private upper bound, so that like it's in some sense differentially private in 2 ways. Okay, and also this is what people do, like in the first place. You basically run stochastic gradient, and then you add a calibrated sequence of noise to your gradient.
I have another question. So you do need that your samples are drawn IID, right?
Yeah.
So for example, if I wanted to formulate asymptotic consistently in a network setting as the number of nodes go to infinity where I don't have independence, then that's zero.
Then it doesn't work. Yeah. But then you can consider 2 separate problems where you resample the whole thing and then calculate the generalization by the structural loss. Yeah. When you sample like a network of the same size, you can also calculate the generalization and how well you do with that given number of size of the network. Yeah. So and we tried that on Netflix data, and yeah, it worked really well. I mean, really well in the system sense. In terms of privacy, we can, like with a sacrifice of about like 15% of the accuracy, we are able to get this epsilon differential privacy loss to about like 1 or something.
Yeah. Epsilon is 1 or epsilon?
Yeah. Epsilon is 1, and we suffer like a 15% loss.
Wait, epsilon's 1, the privacy has, so that means probability.
No. He's got the log. He defines it a little differently than we did with the log.
Yeah, but it's like it's the same.
That the probability of failure is 1 minus 1 over.
Yeah, right. That's like the marginal case of whether this epsilon is meaningful or not meaningful. Yeah. When epsilon is much larger than 1, then it doesn't really make sense to talk about differential privacy. So there are also bad news. A lot of problems are not actually privately learnable. So the picture may well look like this. So one of the examples that people came up with is the learning of threshold functions. That's VC dimension 1, meaning that in the non-private setting, you can learn it with a constant number of data points, random samples. And this is actually quite a dense set. So for all the learning problem in the continuous domain, when the loss function is discontinuous with respect to the argument in H, then you can basically state the same result. And that's bad because although we can learn things by just running private ERM, but the kind of things that we can learn more or less restricted to the class of problems that has Lipschitz loss function. Yeah.
Is that somehow though like order of quantifiers? Like, I mean, if you pick the distribution on unlabeled points and you fix that, then it will eventually go to zero.
Yeah. If you fix the distribution, then it will eventually go to
Even
zero.
on
But this
even
requires
on examples, even on anyway.
Yeah, this needs I'm just saying that rate can be arbitrarily bad. Yeah.
So wait, is this a theorem? Is it a theorem that if you not Lipschitz, then because the theorem in one direction is Judd, McIver, and Sherry, that if it's Lipschitz, then the exponential mechanism gives you epsilon differentially private.
Yeah, we don't have a lower bound. No. Yeah, we also have the same upper bound.
But you said essentially.
It's
If
got
it's not
counterexamples.
There's some counterexamples, but
Yeah,
we
if
don't know
it's-
in general.
Yeah, if it's not if it's discontinuous, then yeah.
Then we know.
Then we know that you can't
So
do it.
between Lipschitz and discontinuous, you don't know.
Right.
If it's held up with alpha equals 0.1, we don't know.
No, we don't know. Yeah.
So in particular, this means we care about the class of the 0-1 loss. And
Right. For 0-1 loss, and basically in continuous domain, or as long as the number of the size of H is sufficiently large, then basically there's nothing you can do. Yeah. So one may wonder whether epsilon delta differential privacy would help over here. Of course, this depends on how fast that we require this delta to go to 0 as a function of n, and we show that suppose this delta requires to be like relatively large, then we don't require very strong privacy guarantees, and anything that's learnable is also approximately differentially private learnable. But that's bad because like when this thing is large, then we can just pick a random data point and then just output that, and that's not private at all. So it's really bad.
I see.
It turns out,
because approximately
Right.
allows
Yeah.
me to be
Right.
the exception.
Right.
Yes.
Yeah.
Good.
It turns out there's a sharp phase transition. So whenever we require this delta to be on the order of 1 over n, then the same lower bound would apply. Then nothing, things can be learnable, but there doesn't exist any approximately differentially private learning algorithm to actually learn it. Yeah. So this is due to a result of Mark Bond for characterizing the sharp rate of learning threshold functions. Yeah. So the story so far is that in general learning setting, although we can do private ERM and try to learn all the learnable problems, but many problems are not privately learnable. And epsilon delta DP does not help. So doesn't this new thing called concentrated DP, because it's essentially equivalent to epsilon delta DP. Yeah, the thing is, even if a problem is privately learnable, like we didn't say anything about the learning rate, it might not be practical at all. So when I was like traveling on different conferences and talked to census people and other people who actually deals with the data and use privacy tools to try to come up with value, they are very frustrated with differential privacy. Like, to be honest, and often you need to add too much noise. It ruins the inferences, and it gives really poor utility. And in order to make it work, like when we try to do this Netflix example, it took us a lot of effort to come up with tricks like clipping and rescaling to ensure that the loss function is bounded by a not too big number, and to manipulate individual data in a differentially private way so that the whole thing stays differentially private and give meaningful results.
Now also with epsilon equals 1, I mean, I wouldn't be willing to give you my social security to guarantee privacy with epsilon equals 1.
Well, there are different level of comfort for you. Like we have a notion called personalized privacy. We can allow every user to indicate their comfortable level of epsilon, and we can adjust that. Yeah, for every person separately. So,
Okay.
so if you set your epsilon to be really
-10
small, then like 10 to the power of -20, then essentially we are dropping our data off the training algorithm completely. Yeah. So, the reason of all these is because differential privacy is the worst case guarantee. It protects the worst possible data sets. Like it's independent. It's completely independent to the distribution that you join the data from. And it only has something to do with the domain that your data can possibly be from. So it's sensitive to even one outlier in the population and one peculiar data set you can construct from the given domain. So let me illustrate it with a simple linear regression. Suppose every user is X and Y feature and label, and we have 100 of them. Assume X and Y are inside this box so that differential privacy would apply. And we want to just fit a linear regression. This is the simplest possible data analysis task that people could try to do, but still it poses a big challenge for differential privacy. Like we also need to assume the space of the coefficients are bounded so that the loss function is uniformly bounded from above. All right. So what we do is to just release through the posterior sampling by adjusting this gamma. We'll plot the privacy loss for every single gamma. So here's what it looks like. So this is like this purple line is the access risk. That's the actual like utility of this learning algorithm that gives you. And this is like the estimate of the generalization error.
Lower is better for X?
Yeah, lower is better. Lower is better for everything. So the x-axis is just this gamma. When gamma is larger, it means more utility and less privacy, and the other way around. And this line is the loss epsilon, the differential private loss. Like due to previous discussion, like whenever this is greater than 1, that's here, it becomes more or less meaningless. So this basically means that at the intersection, if we want a non-trivial differential privacy guarantee, then we lose by 100 times in terms of utility. So it's very hard to minimize the empirical risk when you require differential privacy. So that's bad. So people have been trying to solve this problem, but not by a lot, because they are not willing to give up the distribution freeness of the definition of differential privacy. So the second question that we pose, let me check how much time I have. Okay, 10 minutes.
We started a little late,
okay.
So if we run over like 5 or 10 minutes,
okay,
that's fine.
All right, great. So is there some much weaker notion of privacy that we can define, which preserves the provable privacy guarantees in the weak sense, inherit most of the desirable properties of differential privacy, and at the same time give us a lot more utility in practice? Is there such a definition? So that's the discussion of the last part of the talk. So recall that the definition of differential privacy has 2 supremum over here. The on-average KL privacy, this is called by Leibler divergence KL, simply replaces both supremum with expectations. So the second expectation is taking over your randomized algorithm, and the first expectation is taking over the distribution of the data set, as well as this small perturbation that changes your data set by 1 row. Okay? So
okay,
this.
I sort of would probably be fine as a user with the second expectation, but the first one you are, for example, saying, okay, I assume this movie set has been generated by some generative model where I assume independence and then I say to you, that's fine if you want to do learning, but if my privacy depends on that Netflix has been exactly generated like that, both you and I know it's not true, and now your guarantee is 0.
So the question boils down to whether the adversary can condition on this data set V.
No, but you give me a guarantee which is not a theorem anymore, because we both know that not even adversary, just because we know how the Netflix data set is being generated. And
I claim that
the way
yeah,
you claim.
I claim that this notion of privacy, or like more reasonably a stability notion, it protects a typical user joined from the same distribution with sufficiently high probability. Yeah. So that's the only claim that I'm not trying to protect everybody, because there are people that do not care about privacy. And yeah, please just bear with me, and let's go to like a really weak notion of privacy. I know people wouldn't like it, especially like you and Cynthia. But yeah, but let's just bear with me and see like what we can say about this new notion of privacy. So again, like the second part is KL divergence. We can replace this with a soup and with something in between, and the differential privacy is essentially the maximum of the max divergence, and this is just a different measure of the difference of the two distributions. Okay?
Yeah.
So it measures the average privacy loss, and this obviously unaffected by pathological cases, because we are essentially defining a different epsilon for every data generating distribution. And yeah, and it's stated it's adaptive to every data distribution. And perhaps the best thing about it is that we can now estimate that from the data. In other words, we can now estimate the lower bound of the differential privacy loss just from the data. Okay? What are the other properties? We show that this average KL privacy, it satisfies most of the designing properties of differential privacy, including the small group privacy, like big group as well. And it composes over different multiple access to the data adaptively and non-adaptively, and is also close to post-processing. Okay, so the composition might be a little tricky. Suppose this is a function on the data. This is epsilon OA KL private, and there's another function that possibly depends on the F. So condition on the outcome of F, we can now come up with a new thing. And it is also randomized, so we can say that it is on average KL private, but now this epsilon would depend on F. Okay, so the composition would say that suppose jointly these two procedures will give you epsilon plus the expectation of epsilon F, where this expectation is taking over the randomness of F.
Now, if you replaced the first expectation by a soup, you would probably lose much of this, yes?
Yeah. Suppose these are also epsilon differentially private, then
there's something in between. So Jennifer is asking.
I'm asking if you go back to your definition, and as you said, one could imagine keeping the KL divergence, but taking a soup over the data. You would lose a lot of these nice properties, just as standard DP loses a lot.
So Jennifer is asking, what about worst case KL privacy? Have people looked at that?
Well,
people have looked at it.
Maybe we should talk about it during our one-on-one review.
So
I'm sure you've thought of that.
So that definition is also defined, and you still get closeness to post-processing. You still get composition, but you don't get group privacy.
Okay.
So the thing is, we now do not need the loss function to be bounded, because we are sampling from like any given loss. And that's actually the case when we do a Bayesian model, and we don't specify a boundedness of the loss function. But when the loss function is indeed bounded, then the same algorithm would give you differential privacy. So this means that like there are two different ways of looking at the same randomization within your learning algorithm. Like if it is DP, the epsilon might not be very small, but we can evaluate it in a different way and give you a different interpretation in terms of on average, what's the privacy loss of a typical user, and that's going to be orders of magnitude smaller than DP. What's more interesting is that if we restrict our attention to the class of posterior sampling algorithm, then this notion of privacy actually characterizes a notion of generalization called on-average generalization. Yeah, so recall that previously this expectation is outside the absolute value. Now if we push it back in, like we only need this to show like an algorithm is consistent, and epsilon on average KL privacy actually characterizes the generalization error. Yeah, like for each distribution separately. Okay, so this is really cool. So a corollary is that suppose we scale this loss function somehow, then it's equivalent to defining a new loss function that's just a fraction of the original one. And we can use on average KL privacy to, that's epsilon, to calculate the on average generalization error. And also vice versa. We can estimate privacy by estimating generalization. We can estimate generalization by estimating privacy. Yeah. So let's revisit the linear regression example that I showed you guys earlier. Like this is everything that's on the previous slide. What would on average KL privacy be here? Yeah. By the way, like the differential privacy epsilon is the upper bound of the generalization error, so there's no issue. Here's where it is. So the red line is on average KL privacy. As we can see, from the worst case to the average case, we save 4 orders of magnitude of utility. Now we can, at the same place where this epsilon equals to 1, we can get like nearly identical performance, like only a small loss from the right-hand side in terms of the access risk. And also, since I showed you that on average KL privacy characterizes generalization, if you appropriately rescale it, like this is the estimation of generalization error through privacy, and we use the same number of rerun of the experiments. As we can see, we get a much lower variance comparing to if we estimate the generalization directly. Yeah, and the theorem doesn't break because it's just, yeah, the generalization and KL privacy and expectation are exactly the same. Okay, so in summary, we defined a new definition of privacy called on average KL privacy, and we requires no changes in the algorithm. It provides average case privacy and is practically meaningful in the average case, especially when epsilon in DP is too large. And even infinite, we can still get non-trivial results for this on average notion of privacy. It characterizes the generalization for posterior sampling, and I think it's a necessary step that we have a way to empirically measure privacy if we want to really use it in practical applications. So yeah.
You can 5 more minutes.
Okay. Okay. So I'll have a few minutes to talk about the future work. What I plan to do, like maybe 2 years to 5 years from now. So first of all, I think the results and this general topic that I presented just now is a really exciting field to be in because everybody nowadays care about privacy and its intersection with machine learning. Now that we have a way to estimate privacy or a lower bound of differential privacies epsilon in practice, we can try to come up with say a private machine learning competition, just like Netflix. So anyone can submit their own like randomized algorithm, and we come up with a bunch of data sets that people care about in practice, and then evaluate the privacy and utility of your algorithm and tabulate it, so that this can be a competition that brings together practitioners and theorists, because like the way we evaluate privacy can be like essentially the same as what differential privacy protect against. We can run a deep neural network to try to identify individual users by feeding the output of the internal state of your released deep networks, and then substitute in data points, and then you get a really high-dimensional feature vector. Then we can try to classify the feature vector with respect to whether that particular individual is used to train the network or not. And if we can do that, then it means that it's not private. And if we can't, even if we are using the state-of-the-art machine learning classifier, then it's likely that, like, because we are already having the most relevant site information and we're using the best tools available so far, then I would claim that in practice, like, this randomized algorithm is pretty good. It's pretty secure. Yeah. So Vitaly Shmatikov has like some preliminary results on this, like using deep learning to beat deep learning, to beat private deep learning and things like that. Yeah. So it's really cool. And another thing that as a take-home message from the sequence of research that I did is that statistical tools can be really useful to boost the accuracy and utility of differential private release. So one of the things people can do is to do a post-processing, because optimal post-processing, because DP is resilient to any form of data-independent post-processing. And in this case, it's very interesting because we do not actually need to assume a noise model as people often do in statistics. Now we know the noise model exactly because that's from the privacy. We injected that. And also the properties of true functions. Suppose we try to release a histogram, and that histogram is known ahead of time. And usually, in order to tune parameters of certain statistical methods, we do not need the whole data sets. We only need like some functions of the data set. And those like are just scalars, and we can release that like differentially privately. So there's a question of how can we optimize the allocations of the privacy loss over the entire pipeline. And that's like a future research of great interest. I'll show one example of how well you can do when you do post-processing comparing to not doing post-processing at all. And also there are ways to learn from aggregate data, just the summary statistics, rather than requiring the labels to be seen for every data point. So I also show like some of my past research on how can we learn from just label proportions rather than label. We can randomize label proportions by adding a little bit of noise to ensure privacy. Say this can be your political opinion, whether you support Trump or Hillary, and things like that. Yeah. A related field in social science is called ecological inference. So here's an example. So this is a regional data set from one of the motivating applications, that's the New York City taxi data. So I'm plotting the number of taxi pickups snapped to the nearest street corner of Manhattan. And this is a regional data that we try to release. All right? So how do you release that privately? What you can do is, because like at every hour, every taxi driver can at most pick up, like say, 2 or 3 jobs. Then you can just add noise to every bin with variance, with standard deviation proportional to that like limit number of the number of tasks people can do. Okay, so that gives us this differentially private release. So for people who know my work, I also work on non-parametric regression. In particular, this locally adaptive non-parametric regression on graphs. Okay, so we can just plug in like this DP release, which is a noisy, perturbed version of the original data, to a non-parametric regression smoothing technique, and get this. If we compare the original data and the denoised DP release, I would argue that like this reveals more information and are cleaner. It even denoise the original data. So if we measure the utility in a different way, by assuming original data is also generated randomly with some intrinsic noise, then I would claim that by doing post-processing, we can even get a cleaner picture than the original data. And because of its differentially private release, that guarantees generalization. So we get the best of both worlds, like in this sense. Yeah. So for learning from label proportions, here's our analysis on the election results from these colors are results from the exit polls in the 2012 election between Obama and Romney. We have an updated version for Hillary and Trump, but that's not public yet. Yeah, so the task is like based on only basically we know the label proportions for every electoral regions, and we also have the individual level data from the Census Bureau. And what we did here is to combine these two informations and try to run ecological inference so that we can fill in the gaps and get a finer picture of the results for women's in every electoral region across the United States. Yeah. Our ecological inference is to try to it's like a Simpson's paradox. So you try to learn a more fine-grained statistics of the data by only observing the total summary statistics. Like you can't do that in general, but with additional assumptions, conditional independence assumptions, you can do that provably. Yeah. So this is one example of ecological inference. So as we can see, these results are pretty consistent in the states where we do have the exit polls, and there are a lot of additional data that additional inferences that we can run, and yeah, we really need to have some political scientists to look at this picture and see what are the things that they can stories that they can tell from this. Anyways, we can also use privacy to help machine learning and statistics because the type of generalization that's provided by privacy and maybe just randomization is a more robust notion of privacy that's resilient to p-hacking. All right, and we can use it to somehow automate the entire pipeline of learning. So, in conclusion, in this talk, I showed you guys that privacy and learning are intimately related tasks through generalization. And the same randomization can give you different interpretations of how much privacy that you lose. And I think it's an exciting field, and I will be very happy if I hopefully get an offer. I can join you guys and work on these problems together. Yeah. Thank you.